ENSO, short for El Niño, a southern oscillation, is not a single weather event and not just an ocean temperature map turning red or blue. It is a coupled climate pattern linking the tropical Pacific Ocean and the atmosphere above it. That coupling matters because the tropical Pacific is enormous and sits near the center of global heat and moisture exchange. When ENSO shifts phase, it can alter where rising air, clouds, and heavy rainfall prefer to form. Those tropical changes then ripple outward through atmospheric circulation, influencing weather risk far away. This is why ENSO is discussed by farmers, fisheries managers, insurers, and disaster planners, not only by climate scientists. It is a recurring source of internal climate variability that can temporarily push conditions warmer or cooler globally while also redistributing flood and drought risk across regions. To make ENSO intuitive, think in three states: neutral, El Niño, and La Niña. Neutral means the coupled ocean atmosphere system is near its baseline range, with normal trade wind strength and typical east-west Pacific temperature contrast. El Niño is the warm phase, where central and eastern tropical Pacific surface waters become warmer than normal. La Niña is the cool phase, with those waters cooler than normal. These states do not occur on a strict timetable. ENSO is irregular, typically appearing every 2 to 7 years, with different durations and intensities each time. Some El Niño episodes become especially intense, some La Niña episodes repeat or persist longer. Neutral intervals between events are not empty gaps, they are periods where the system recharges, redistributes heat, and sets up the background conditions that influence what comes next. The atmospheric side of ENSO is called the Southern Oscillation, a large-scale pressure seesaw across the tropics. During El Niño, pressure tends to be higher than normal over Indonesia, Australia, and across nearby tropical regions, while the pressure pattern over the Pacific shifts in a way associated with weaker trade winds. During La Niña, the broad pattern is roughly reversed, with higher pressure over parts of the central and eastern Pacific and relatively lower pressure across much of the remaining tropics and subtropics. Why does this pressure story matter? Because pressure gradients drive wind, and wind controls how warm surface water is arranged across the Pacific. So pressure is not a side note. It is one half of the mechanism. ENSO is fundamentally a dialogue between atmospheric pressure and ocean temperature, each continually reshaping the other. At the ocean surface, trade winds are a key control lever. Under typical conditions, easterly trade winds push warm surface waters westward, helping maintain warmer waters in the western Pacific and relatively cooler conditions in the east, where upwelling brings cooler, nutrient-rich water upward near the equator. If those easterlies weaken, warm water can spread eastward, and upwelling in the eastern equatorial Pacific is reduced. Less upwelling means less cold water reaching the surface, so temperatures there rise further. That warming changes atmospheric convection and cloud rain patterns, which then weakens winds more. This is the core transition pathway into El Niño-like conditions: wind weakening, eastward warm water shift, reduced upwelling, and additional warming. Each step reinforces the next, showing why even modest disturbances can grow into basin-scale anomalies with global weather consequences. This amplification loop is often described through the Bjerknes feedback. The principle is simple but powerful. Ocean warming in the central eastern Pacific weakens the normal atmospheric east-west circulation, commonly framed through a weaker Walker circulation. A weaker Walker circulation corresponds to weaker trade winds. Weaker trades then allow more eastward spread of warm surface waters and further suppression of cold upwelling, which reinforces the initial warming. That is positive feedback. But ENSO events do not intensify forever. Over time, heat reservoirs are redistributed and depleted in ways that reduce the original anomaly, and delayed ocean atmosphere processes begin to oppose it. Event decay and phase transition are still active research areas, which is one reason ENSO prediction remains probabilistic rather than deterministic. The system is dynamic, coupled, and nonlinear, so timing and magnitude can shift significantly from one event cycle to another. Once tropical heating patterns shift, teleconnections carry the signal outward. Teleconnections are long-distance links where anomalies in one region alter circulation and weather probabilities elsewhere. Under ENSO influence, some areas face elevated flood risk from heavier or more persistent rainfall, while other regions become more drought-prone due to suppressed precipitation. Importantly, ENSO tilts odds. It does not pre-write every storm, heat wave, or dry spell. Local geography, other ocean basins, and shorter-term weather dynamics still matter. But probability shifts can be large enough to change outcomes across seasons. For decision-makers, this means ENSO information is most useful as risk guidance. Not this exact event will happen on this date, but the seasonal distribution of likely outcomes has changed, and preparedness choices should adjust now. That framing supports better planning for water storage, crop timing, health services, and emergency response capacity. ENSO also modulates global mean surface temperature on short timescales. El Niño phases often coincide with temporary warming spikes because ocean heat release to the atmosphere increases. La Niña phases often coincide with short-term cooling influences, as the ocean atmosphere exchange pattern shifts in the opposite direction. This variability can shape the apparent pace of warming over several years, especially on roughly decadal windows where the relative frequency of warm versus cool ENSO phases changes. But this is variability around a trend, not a replacement for the trend. Long-term global warming from greenhouse forcing continues underneath. A helpful analogy is a rising escalator with people stepping up and down. ENSO drives many of those steps, while external forcing sets the escalator's upward direction. Misreading ENSO-driven swings as long-term reversals leads to poor interpretation of climate signals and policy risk. The social and economic stakes are especially high in developing countries bordering the Pacific, where agriculture and fisheries often carry heavy livelihood weight. In farming systems, ENSO-linked shifts in rainfall timing can be as damaging as changes in seasonal totals. Late onset, long dry gaps, or intense rainfall bursts can each undermine yields through different pathways. In marine systems, altered upwelling and temperature patterns can affect nutrient availability, ecosystem structure, and fish distribution, pressuring communities dependent on stable catches. Infrastructure and governance capacity determine whether climate stress becomes manageable disruption or severe crisis. So ENSO should be treated as a risk multiplier interacting with vulnerability. Better early warning is necessary but not sufficient. It must be paired with local adaptation capacity, practical response plans, and financing tools that allow action before losses cascade across food security, household income, and public health. A common source of confusion is why one agency may declare El Niño while another sounds more cautious. The reason is methodological differences, not necessarily scientific contradiction. Monitoring centers use different threshold definitions, regions, averaging windows, and atmospheric confirmation criteria depending on their operational goals. Some definitions emphasize sea surface temperature anomalies in specific Pacific boxes. Others require sustained coupling signals such as pressure patterns and wind anomalies. Duration rules also vary, so brief anomalies might not qualify in one framework but may trigger a watch status in another. For users, the practical takeaway is to look beyond the headline label and read the confidence level, persistence expectation, and regional impact outlook. Decision quality improves when planners focus on magnitude, duration, and teleconnection implications rather than treating ENSO as a binary on-off switch. Forecasting ENSO remains difficult because the system depends on coupled processes across ocean surface, subsurface heat content, and atmospheric circulation. Small errors in initial conditions can grow over months, and predictive skill is not uniform through the year. Even so, forecasting has improved through denser observations, better data assimilation, and multi-model ensemble approaches that estimate probability ranges rather than single deterministic outcomes. The strength of modern ENSO outlooks is risk calibration. For example, elevated probabilities can justify earlier drought planning, reservoir operations changes, procurement adjustments, and contingency budgeting. Waiting for certainty is often more costly than acting on well-framed probability. In climate-sensitive sectors, lead time is valuable. A forecast that is imperfect but timely can still materially reduce damage when institutions are prepared to translate probabilistic climate signals into pre-agreed, trigger-based actions. How climate change will alter ENSO itself is still an area with meaningful uncertainty, but the impact context is clearer. Current assessments do not support a simple claim that ENSO will lock permanently into one phase. However, evidence indicates that hydrological impacts linked to ENSO can intensify in a warmer world. The IPCC 6th assessment highlights that precipitation variance related to ENSO is very likely to increase over the long term, and that changes in teleconnection strength and spatial extent are likely to produce significant regional consequences. In practical terms, this means variability matters even more under warming. Adaptation cannot focus only on average climate shifts, it must address swings, extremes, and compound hazards like drought followed by flood. Systems designed for yesterday's variability envelope may underperform as ENSO-linked rainfall volatility and regional impact patterns evolve. The essential picture is that ENSO is a repeating planetary reorganization of ocean heat and atmospheric circulation, not a niche-specific curiosity. El Niño and La Niña are opposite expressions of the same coupled engine, and the southern oscillation is the atmospheric pulse connected to that engine. Through feedbacks like the Bjerknes mechanism, local anomalies can scale up. Through teleconnections, tropical shifts can reshape risk globally. Through short-term temperature modulation, ENSO can speed up or slow down apparent warming for a few years without altering the long-run climate trajectory. The most useful way to apply ENSO knowledge is probabilistic and strategic. Monitor evolving phase conditions, map likely regional impacts, and act early where exposure is high. Communities that treat ENSO as actionable risk intelligence, rather than background trivia, are better positioned to reduce losses when the Pacific climate engine shifts again. If you found this helpful, please like this video and subscribe for more explainers.